Good morning, everyone. Thank you for joining us today.
Good morning. Great to be here.
Last time, we really got into the weeds, peeling back the layers on how our devices actually talk to each other. Today, we're zooming out a bit, looking at the colossal digital brains that turn all that raw data into something genuinely useful. This isn't just about sensors anymore. It's about the intelligent platforms, the cloud infrastructure that, really brings the connected world to life.
Yeah, building exactly on our last deep dive into communication protocols for Internet of Things, we're now kind of ascending to the higher layers of the IoT stack. It's the next logical step. Our mission today really is to provide a comprehensive Q&A overview on Internet of Things, platforms, and cloud integration. And to guide us through this, I thought it best to lay out our roadmap first. We'll cover the foundational elements all the way to the critical connections that stitch everything together. So here are the questions we'll tackle. 1, can you explain the 3 main cloud service models, iOS, PaaS, and SaaS? 2, which of those models is most relevant for IoT platforms? Pretty crucial. 3, what are the core services offered by Amazon Web Services, AWS IoT? 4, what about Microsoft's offering, Azure IoT? How does it position itself in the market? Where does it fit? 5, how does the Google Cloud IoT platform differentiate itself from the others? What's their angle? 6, then in contrast to these hyperscalers, what is a platform like Blank and who is it really designed for? 7, we'll look at the data lifecycle. What happens during the first stage? Data ingestion. 8, and then what happens during the data processing stage? 9, what are time series databases and why are they, seemingly ideal for IoT? 10, what about other types of data? What are data lakes used for? We hear that term a lot. 11, what's the difference between real-time and batch analytics? Key distinction there. 12, what role do application programming interfaces, APIs, play in IoT? Think of them as translators. 13, can you give some examples of how APIs connect the different parts of the system? Make it concrete. And finally, number 14, what is the key takeaway about the role of IoT platforms and the cloud in this whole connected world picture?
Wow, okay. That is quite a roadmap. It really covers the landscape from top to bottom. It definitely highlights how crucial this whole area is for anyone really trying to grasp the full picture of IoT. Let's jump right in. So before we even talk specific IoT platforms, it feels essential to understand the cloud service models they're built on. We hear these acronyms constantly: IoT, PaaS, SaaS. Can you break those down for us? How are they different? And why does that difference actually matter for IoT development?
Absolutely. It's a perfect starting point because these acronyms, they represent different levels of abstraction in cloud computing. And that dictates how much control you have versus how much the cloud provider manages behind the scenes. So IS, infrastructure as a service, this is the most, let's say, foundational level. The analogy I like is leasing a plot of land. You get the land, but you have to build the entire house yourself: foundation, plumbing, wiring, everything. The provider gives you the basic computing resources, think of virtual machines, storage, networking on demand, but you're responsible for managing almost everything else: the operating system, any middleware, your application code. Now, for IoT, this gives you maximum flexibility. You can build a completely custom backend.
Okay, so total control, but also sounds like a lot of work.
Exactly. It comes with a significant management overhead. You're managing servers, patching OTs, all that stuff.
Right. So with IS, you get the raw ingredients, but you're the master chef building it all. What about PaaS then? How does that change things?
The PaaS, platform as a service, is a step up in abstraction. Think of it like renting a fully equipped workshop. The provider manages the underlying infrastructure, the servers, the operating systems, the networking, the physical building itself, and they offer you a platform, essentially a set of integrated tools and services specifically for building, deploying, and managing your applications. So you focus purely on your application code and your data, not the underlying plumbing.
Ah, okay. That sounds much more streamlined for development.
It is. And for IoT, this is often the sweet spot. Providers offer specialized IoT PaaS services things for device connectivity, data ingestion, device management right out of the box. It accelerates things significantly.
Makes sense. And then the last one, SaaS, that's the fully finished product, right?
Precisely. SaaS, software as a service, is the most abstracted model. Here, the provider delivers a complete, ready-to-use software application over the internet. You just subscribe and use it. The analogy here is moving into a fully furnished service department. Everything's handled for you. In the IoT world, a SaaS offering might be something like an off-the-shelf asset tracking solution or maybe a smart home management app you just sign up for.
Got it. So iOS is build it yourself, PaaS is build on their platform, SaaS is just use their app.
That's a great way to summarize it. And what's really interesting, especially in sophisticated IoT solutions, is that you often see a blend of these models. You might use an IoT PaaS for the core device communication and data handling, maybe some IaaS for highly custom, heavy-duty data processing, and perhaps a SaaS application for the business users interacting with the final insights.
That blending makes a lot of sense for complex systems.
Okay.
So given those three models, our second question was, which one really forms the backbone of most dedicated IoT platforms that developers are using today?
Right. When we talk about these specific IoT platforms, the ones designed to make building IoT solutions easier, we are overwhelmingly talking about a specialized form of platform as a service.
Okay, so PaaS is the key here.
Yes. These platforms bundle those pre-built services we mentioned: device connectivity, secure data ingestion, device management, rule engines, and so on. The huge benefit is you're not building those fundamental back-end services from scratch. Imagine trying to build a system to handle millions of MQTT connections securely. That's a massive undertaking. PaaS handles that, which, as you said, dramatically accelerates development time. It lets teams focus on the unique value their specific IoT solution provides, not the generic infrastructure.
That's a massive time saver, absolutely. It really clarifies why these platforms have become so central to IoT development. Now, speaking of popular platforms, let's move to question 3 and talk about the giants, the hyperscalers. When you think cloud scale and breadth, Amazon Web Services AWS IoT often comes up first. What are its core services? What's their strategy, their play in the IoT space?
AWS, yeah, being the overall cloud market leader, they definitely have an incredibly mature and feature-rich IoT ecosystem. It's very comprehensive. At its absolute heart is AWS IoT Core. You can think of this as the central managed cloud gateway. It's designed for massive scale, handling billions of devices and trillions of messages. It provides secure device connectivity using standards like MQTT and HTTPS. It also includes things like a basic rules engine for routing messages and a device shadow service.
Device shadow, what exactly is that?
Good question. The device shadow is basically a virtual representation, like a digital twin, of a device's last reported state stored in the cloud. So an application can interact with the shadow even if the actual device is offline temporarily. It can query the last known temperature, for instance, or set a desired state that the device will pick up when it reconnects.
Okay, interesting. So IoT Core is like the central hub for device communication state.
Yeah.
You also mentioned extending intelligence out to the edge.
Exactly. That's where AWS IoT Greengrass comes into play. Greengrass essentially extends AWS cloud capabilities out to the edge devices themselves. This allows devices to run AWS Lambda functions locally, perform local data processing and aggregation, make decisions faster, and, importantly, operate even with intermittent or unreliable connectivity back to the main cloud. And beyond Core and Greengrass, AWS has this vast ecosystem of tightly integrated services. Things like IoT Device Defender for security posture management, IoT Analytics for, analytics, S3 for storage, and SageMaker for building and deploying machine learning models, often trained on IoT data. It's designed as an end-to-end solution.
Impressive scale and integration, definitely the AWS hallmark. Okay, let's pivot to the next hyperscaler for question 4. Microsoft. How does Azure IoT position itself differently in the market? What are its key offerings?
Microsoft's Azure IoT platform plays heavily on its strengths in the enterprise space. Its real differentiator is often seen as its seamless integration with existing Microsoft business systems, things like Dynamics 365, Power BI, the whole Microsoft ecosystem. The core service, analogous to AWS IoT Core, is Azure IoT Hub. It acts as that central message broker for secure, bidirectional communication between millions of devices and the cloud backend, reliable and scalable.
So a similar core function to IoT Core, but with maybe a stronger enterprise integration story.
That's often the perception, yes. And for organizations looking for an even faster on-ramp, Azure offers Azure IoT Central. IoT Central is actually a higher-level SaaS offering. It simplifies the whole process with pre-built application templates for common IoT scenarios, like connected factory or smart building management. It lowers the barrier to entry quite a bit.
And I recall hearing Azure has a particular focus on security, especially right down at the silicon level. You mentioned that earlier.
Yeah.
Can you elaborate on why that's so critical for their target enterprise market? What's a unique challenge they tackle there?
You're absolutely right. Azure places a very strong emphasis on end-to-end security, and Azure Sphere is a prime example. It's not just software, it's a holistic solution. It includes a specific certified microcontroller chip, a custom hardened Linux-based operating system, and a cloud-based security service that monitors and updates these devices. The goal here is to create highly secure, trustworthy connected devices right from the hardware foundation. For enterprises deploying potentially millions of devices that might be in the field for years, ensuring they aren't vulnerable attack vectors is paramount. It addresses that huge challenge of securing the device itself, not just the cloud communication.
That makes sense. Building security in from the trip up.
Precisely. And similar to AWS Greengrass, Microsoft has Azure IoT Edge, which allows organizations to deploy cloud logic, Azure services, and AI models directly onto edge devices. This enables local processing, lower latency, and reduced bandwidth costs.
Okay, so if AWS leads with, say, breadth and market maturity, and Azure excels with enterprise integration and that deep device security story, where does Google Cloud fit in? Our fifth question. How does Google Cloud IoT differentiate itself? What's their unique strength?
Google's platform really shines by leveraging its world-renowned expertise in data, analytics, and particularly machine learning. That's their home turf. Now, it's worth noting their specific strategy around their original IoT Core product has shifted more towards partner-led solutions recently. However, the underlying Google Cloud services that support IoT workloads remain incredibly powerful. For instance, Cloud PubSub is their global real-time messaging service, excellent for scalable data ingestion. And then there's BigQuery. BigQuery is a, frankly, formidable serverless data warehouse. It's known for its ability to run complex analytical queries over massive data sets. We're talking petabytes with remarkable speed.
So it's less about a specific IoT platform product maybe, and more about leveraging their best-in-class data tools for IoT use cases, like a launchpad for deep intelligence.
Exactly. That's a great way to put it. Google's strength is inherently data-centric. Their platform is a natural fit for IoT applications that demand sophisticated, large-scale data analytics, maybe training complex AI models using services like Vertex AI, or driving comprehensive business intelligence dashboards. If your IoT solution is fundamentally about transforming those raw sensor signals into deep, predictive insights or strategic foresight, Google Cloud offers a very compelling, powerful environment for that kind of work.
Makes sense. Focus on the intelligence derived from the data. But, as you hinted, not everyone needs that kind of hyperscale power, especially early on, or for simpler projects. Which brings us to question 6. What about a platform like Blink? Who's that designed for, and how does it contrast with these giants?
Blink. Yes, it offers a really refreshing contrast. It's an IoT platform specifically designed for ease of use and rapid development. It's about democratizing IoT access, really. Its target audience is quite different. Individual makers, hobbyists, students, but also small and medium-sized businesses or even larger companies doing rapid prototyping who need to get a product or a proof of concept up and running quickly without a huge back-end team.
Okay, so ease of use is key. For someone maybe new to IoT development, how much of that steep learning curve does something like Blink really remove? And what's maybe the most common aha moment beginners have with it?
It removes a significant amount of the complexity curve, particularly around the cloud backend and the user interface development. Blink provides a low-code or even no-code environment. A core feature is its drag-and-drop mobile app builder. You can literally piece together an interface for your project on your phone. It also has a web dashboard builder and very straightforward device management tools. The aha moment. I think it often comes when someone connects their microcontroller, maybe an ESP32 or a Raspberry Pi, sends some sensor data, and within literally hours, they have a functional, professional-looking app on their phone controlling their project or displaying data. They realize they didn't have to write complex server code or native mobile apps. Blink abstracts away so much of that back-end and front-end complexity. It's a fantastic example of an IoT PAPA's laser-focused on developer experience and speed to market.
That sounds incredibly empowering for makers and smaller teams. Getting a working prototype that fast is huge. Okay, let's shift gears now and follow the data itself. Once a device is connected using one of these platforms, data starts flowing. Question 7. What actually happens during that first stage of the data lifecycle, known as data ingestion? What does that involve?
Right, data ingestion. It's the critical first step, the front door for device data entering the cloud platform. This is where those gateway services we talked about, like AWS IoT Core or Azure IoT Hub, come into play. They act as highly available, highly scalable endpoints designed to handle potentially millions of simultaneous device connections sending data.
And security must be absolutely paramount right at this entry point, I imagine.
Paramount is the right word. The ingestion point is responsible for authenticating every single device that tries to connect. Usually this is done using cryptographic methods like X.509 certificates unique to each device. It also ensures all communication is encrypted, typically using TLS, transport layer security, the same standard that secures websites. This ensures only authorized devices can send data, and that the data itself is protected while in transit from the device to the cloud. These gateways are also optimized to handle the standard IoT communication protocols, primarily MQTT because it's lightweight and efficient, but often also HTTPS for devices that need web-like interactions.
Okay, so secure, authenticated, encrypted entry. Makes sense. Once that raw data is safely inside, it probably isn't immediately useful. Question 8. What happens during the next stage? Data processing. How is that raw data transformed?
You're right. Raw sensor data, just streams of numbers or simple status flags, often needs context or transformation to become meaningful. The data processing stage is all about filtering irrelevant data, enriching it with other information, performing calculations, and routing it to the right downstream services. Most platforms include simple rule engines first. Think of the AWS IoT rules engine. These let you define basic conditional logic. For example, if the incoming message is from temperature sensor T1AA, the temperature value 40 degrees C, then trigger an alert notification, and store the reading in the database.
So basic in that logic for immediate actions or simple routing. What about more complex operations, especially in real time?
For more complex processing, especially on data that's flowing continuously, you often feed the ingested data streams into specialized stream processing services. Examples would be Amazon Kinesis or Azure Stream Analytics. These tools are designed to perform more sophisticated transformations, aggregations over time windows, like calculating the average temperature over the last minute, anomaly detection, and other analyses while the data is still in motion. And for completely custom logic, things that don't fit neatly into rules or standard stream operations, serverless functions are incredibly powerful. Services like AWS Lambda or Azure Functions allow you to write small snippets of code that get triggered automatically by incoming messages. For example, a Lambda function might trigger when a device reports its ID, look up that device's installation location from a database, add the location data to the message enrichment, and then forward the enriched message for storage. It's all about turning those raw signals into usable, actionable information.
Filtering, enriching, analyzing in motion. Lots happening there. After processing, this now more valuable data needs a place to live. Question 9 brings us to storage. What are time series databases, and why are they considered so ideal for IoT data?
Yeah, storing IoT data efficiently is crucial. For telemetry data, which is the bread and butter of many IoT applications, essentially sequences of measurements taken over time, like temperature readings every 5 seconds, vibration data from a machine, energy consumption time series databases, TSDBs, are specifically designed. Think of services like AWS TimeStream or Azure Data Explorer, or open source options like InfluxDB. What makes them ideal? They are fundamentally optimized for handling massive volumes of data points where each point has a timestamp. Their internal structure, indexing strategies, and query languages are all built around the time dimension. This makes storing billions of timestamped records very efficient, and more importantly, querying that data based on time ranges, for example, show me the average pressure between 2 p.m. and 3 p.m. yesterday, incredibly fast. Traditional relational databases just aren't built for the specific data shape and query pattern at IoT scale.
Okay, so specialized for that constant stream of timestamp measurements. Makes perfect sense. But IoT isn't only time series data, right? You might have device logs, configuration files, maybe images or video. Question 10. What about other types of data? Or if you just want to keep everything, what are data lakes used for in this context?
That's a great point. You often have a mix of data types, and sometimes you want to store the raw, unprocessed data for potential future analysis, even if you don't know exactly how you'll use it yet. That's where the concept of a data lake comes in. For long-term, highly durable, and cost-effective storage of vast amounts of data, structured, semi-structured, unstructured, raw, a data lake is the standard approach. Typically, services like Amazon S3, simple storage service, or Azure Blob Storage are used as the foundation for data lakes. You can basically dump petabytes of data into them in its native format relatively cheaply. The key idea is flexibility. You store everything now, and then later you can apply different processing tools or analytics engines like Spark or query services like AWS Athena or Azure Synapse on top of that data lake to extract insights. It ensures the raw data is available for future batch analytics, compliance purposes, or, crucially, for training machine learning models on large historical data sets. It's like a massive, flexible data archive.
A giant, affordable archive for everything. That's powerful for future-proofing your data strategy. Now, you mentioned batch analytics there, and earlier we talked about stream analytics. Question 11. Can you clarify the fundamental difference between real-time and batch analytics? When would you typically use one versus the other in an IoT scenario?
Yes, this real-time versus batch distinction is critical, and it really boils down to the urgency of the insight or action needed. Real-time analytics, which is often synonymous with stream analytics, is about analyzing data while it's in motion as it's being generated. We're talking about latencies of seconds or even milliseconds. The goal here is to detect patterns, trigger alerts, or make decisions immediately. Think about use cases like detecting fraudulent credit card transactions as they happen, identifying anomalies on a factory production line that signal an imminent equipment failure before it breaks, or dynamically rerouting delivery vehicles based on live traffic updates. Speed is critical. The technologies used here are those stream processing engines we discussed, Amazon Kinesis, Azure Stream Analytics, Apache Flink, Spark Streaming.
Okay, so real-time is about immediate reaction, acting on data now. What about batch then?
Batch analytics, on the other hand, involves processing large volumes of data that is already at rest data that has been collected and stored over a period of time, maybe in that data lake or a data warehouse. This processing happens in discrete jobs, often scheduled to run periodically, say, hourly, daily, or weekly. Batch is used for tasks that are less time-sensitive. Examples include generating complex weekly business intelligence reports summarizing overall trends, calculating monthly utility bills based on accumulated meter readings, or, very importantly, training sophisticated machine learning models using months or years of historical sensor data to achieve high predictive accuracy. For batch, you use tools designed for large-scale data processing like Apache Spark, or query massive datasets in data warehouses like Google BigQuery or Amazon Redshift.
So different tools for different timescales of analysis.
Exactly. And it's important to remember that many sophisticated IoT architectures actually use both. They might use real-time analytics for immediate operational alerts, like a critical temperature threshold being crossed, and batch analytics for deeper, longer-term strategic insights, like analyzing seasonal energy usage patterns. They complement each other.
Right, using the right approach for the right question. That makes sense. Now, connecting all these pieces, the devices, the ingestion gateways, the processing engines, the databases, the applications, requires them to talk to each other. Question 12. The outline called Application Programming Interfaces, or APIs, the Universal Translator. What role do they truly play in holding IoT systems together?
Universal Translator is a great description. If the IoT platform is the brain, then APIs are the intricate nervous system connecting everything. Fundamentally, an API, an application programming interface, is a contract. It's a set of rules and definitions that specify how different software components should interact and exchange data or request services from each other. In the context of a distributed system like IoT, which involves hardware, cloud services, mobile apps, enterprise software, potentially from many different vendors, APIs are the essential glue. They provide standardized interfaces that allow these disparate parts, often built using different technologies by different teams, to communicate and work together seamlessly. Without APIs, it would be chaos.
The glue, the nervous system, the translator.
Clearly.
Clearly vital. Okay, question 13. To make that more concrete, can you give us some specific examples of how APIs connect the different parts of an IoT system, maybe tracing from the device upwards?
Sure, let's walk through a few key API interaction points. First, you have device-to-cloud APIs. The ingestion endpoints we discussed, like AWS IoT Core or Azure IoT Hub, expose APIs. These define exactly how a device needs to format its messages, maybe specifying a JSON structure over MQTT, and how it must authenticate itself, for example, present its X.509 certificate, to be allowed to connect and send data to the cloud. That's an API contract the device firmware must adhere to.
Okay, so the device uses an API to talk to the cloud platform. What about getting data out of the platform or sending commands back?
Right, that's where cloud-to-application APIs come in. Once the data is processed and stored in the cloud platform, your own custom applications like a web-based monitoring dashboard or a mobile control app need to interact with it. The IoT platform provides APIs, very often RESTful APIs using standard web protocols like HTTP, that allow these applications to securely query device data, retrieve device status, view historical trends, and, importantly, send commands back down to the devices through the platform. So when you tap a button in your smart home app to turn on a light, your app is making an API call to the cloud platform. The platform authenticates the request, finds the target device, and uses its connection to relay the turn-on command down to the light bulb itself. That whole interaction is orchestrated via APIs.
Got it. Device to cloud, cloud application. And you mentioned earlier the real enterprise value often comes from connecting IoT insights to other business systems.
Exactly, and that relies heavily on cloud-to-cloud APIs. Modern IoT systems rarely exist in a vacuum. Their true power is often unlocked when the data and insights they generate are integrated with other core business processes and systems. APIs are the enablers here. For example, you could use an API provided by the IoT platform and an API provided by Salesforce, your CRM system, to automatically create a service or maintenance ticket in Salesforce whenever an IoT sensor on a piece of equipment reports a critical fault code. Or, another example, a smart shelving system in a warehouse uses sensors to track inventory levels. When stock runs low, the IoT platform could use an API call to your SAT system, your ERP or supply chain software, to automatically trigger a reorder process. These cloud-to-cloud API integrations are what elevate IoT from just monitoring things to actively driving business automation and efficiency. APIs provide that standardized abstraction layer, hiding the complexity of each system and allowing them to interoperate smoothly.
Those examples really bring it home. APIs are truly the connectors making the whole ecosystem function and deliver business value. Okay, that brings us smoothly to our final overarching question, number 14. Pulling all this together, what is the key takeaway? What's the most crucial thing to understand about the role of IoT platforms in the cloud in our increasingly connected world? What's the big insight?
I think the biggest insight, the key takeaway, is that for any serious, scalable IoT deployment, the cloud-based IoT platform isn't just a component. It is the strategic center of gravity. It's the digital brain, as we've called it, that brings order, intelligence, and ultimately business value to the often chaotic torrent of data flowing from connected devices. These platforms, typically built on that PADIS model, provide a comprehensive suite of tools needed across the entire data lifecycle, from secure ingestion through real-time processing and rules to scalable storage like time series databases and data lakes, and enabling advanced analytics and machine learning. We see hyperscalers like AWS, Azure, and Google providing the immense infrastructure and rich toolsets for global scale, while innovators like Blink show how platforms can also democratize access and speed up development. And as we just discussed, the whole distributed ecosystem devices, edge gateways, cloud services, user applications, enterprise systems is intricately stitched together by APIs, acting as that universal language. However, while these platforms offer tremendous power, they also bring significant responsibilities. Managing costs effectively in pay-as-you-go cloud models is critical. Navigating complex data privacy and sovereignty regulations, especially concerning where data resides, which is a key concern in places like Canada and Europe, is essential. And strategically managing dependencies to avoid getting completely locked into a single vendor's ecosystem is also wise. But perhaps the most provocative thought to leave you with, looking forward. While the cloud provides this essential centralized brain, the future isn't just about centralization. We're seeing a fascinating blurring of the lines between the cloud and the edge device itself. The rise of edge computing, which we'll explore more soon, is pushing more of that cloud intelligence and processing capability outward, closer to the physical world. This is creating more of a distributed computing continuum. So the future likely isn't cloud versus edge, but rather an intelligent, dynamic interplay between the powerful centralized platform and increasingly capable, responsive, decentralized edge intelligence. That interplay unlocks new possibilities for speed, autonomy, and resilience in IoT systems.
That's a fantastic synthesis. The platform is the strategic brain, the importance of the entire lifecycle, the role of APIs is the glue, the challenges, and that really intriguing glimpse into the future with the cloud edge continuum. It definitely gives us a lot to mull over. We've covered an incredible amount of ground today, from those foundational IaaS, PaaS, SaaS models, through the major platform players, the journey of data, analytics approaches, and the vital role of APIs. It really paints a clear picture of how these systems function.
Indeed. It's been a deep dive for sure. We've hopefully clarified how these cloud service models underpin everything, compared the strengths of AWS, Azure, and Google in the IoT space, contrasted them with developer-focused platforms like Blink, followed the data from ingestion through processing and storage understanding, time series databases and data lakes, differentiated real-time from batch analytics, and underscored just how pivotal APIs are. The core message remains. The cloud-based IoT platform is that indispensable digital brain, turning connectivity into intelligence and value, even as we move towards more distributed forms of intelligence. And speaking of distributed intelligence, for our upcoming series, we will delve deeper into precisely that topic, covering edge computing and fog in Internet of Things. We'll explore how and why intelligence is moving closer to the data source. So thank you all for joining us for this deep dive today. Please make sure to subscribe to our channel, Tech AI and Beyond, so you don't miss our next exploration into the future of connected systems.